Random House Audible presents Entanglement, The Greatest Mystery in Physics by Amir Aczel. Read for you by Henry Levya. Preface. My own suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose. J.B.S. Haldane. In the fall of 1972, I was an undergraduate in mathematics and physics at the University of California at Berkeley. There I had the good fortune to attend a special lecture given on campus by Werner Heisenberg, one of the founders of the quantum theory. While today I have some reservations about the role Heisenberg played in history, at the time other scientists left in protest of Nazi policies, he stayed behind and was instrumental in Hitler's attempts to develop the bomb. Nevertheless, his talk had a profound positive effect on my life, for it gave me a deep appreciation for the quantum theory and its place in our efforts to understand nature. Quantum mechanics is the strangest field in all of science. From our everyday perspective of life on Earth, nothing makes sense in quantum theory, the theory about the laws of nature that govern the realm of the very small, as well as some large systems such as superconductors. The word itself, quantum, denotes a small packet of energy, a very small one. In quantum mechanics, as the quantum theory is called, we deal with the basic building blocks of matter, the constituent particles from which everything in the universe is made. These particles include atoms, molecules, neutrons, protons, electrons, quarks, as well as photons, the basic units of light. All these objects, if indeed they can be called objects, are much smaller than anything the human eye can see. At this level, suddenly all the rules of behavior with which we are familiar no longer hold. Entering this strange new world of the very small is an experience as baffling and bizarre as Alice's Adventures in Wonderland. In this unreal quantum world, particles are waves and waves are particles. A ray of light, therefore, is both an electromagnetic wave undulating through space and a stream of tiny particles speeding toward the observer, in the sense that some quantum experiments or phenomena revealed the wave nature of light, while others the particle nature of the same light, but never both aspects at the same time. And yet, before we observe a ray of light, it is both a wave and a stream of particles. In the quantum realm, everything is fuzzy. There is a hazy quality to all the entities we deal with, be they light or electrons or atoms or quarks. An uncertainty principle reigns in quantum mechanics, where most things cannot be seen or felt or known with precision, but only through a haze of probability and chance. Scientific predictions about outcomes are statistical in nature and are given in terms of probabilities. We can only predict the most likely location of a particle, not its exact position, and we can never determine both a particle's location and its momentum with good accuracy. Furthermore, this fog that permeates the quantum world can never go away. There are no hidden variables which, if known, would increase our precision beyond the natural limit that rules the quantum world. The uncertainty, the fuzziness, the probabilities, the dispersion simply cannot go away. These mysterious, ambiguous, veiled elements are an integral part of this wonderland. Even more inexplicable is the mysterious superposition of states of quantum systems. An electron, a negatively charged elementary particle, or photon, a quantum of light, can be in a superposition of two or more states. No longer do we speak about here or there. In the quantum world, we speak about here and there. In a certain sense, a photon, part of a stream of light shown on a screen with two holes, can go through both holes at the same time, rather than the expected choice of one hole or the other. The electron in orbit around the nucleus is potentially at many locations at the same time. But the most perplexing phenomenon in the bizarre world of the quantum is the effect called entanglement. Two particles that may be very far apart, even millions or billions of miles, are mysteriously linked together. Whatever happens to one of them immediately causes a change in the other one. What I learned from Heisenberg's lecture 30 years ago was that we must let go of all our preconceptions about the world derived from our experience and our senses, and instead let mathematics lead the way. The electron lives in a different space from the one in which we live. It lives in what mathematicians call a Hilbert space, and so do the other tiny particles and photons. This Hilbert space, developed by mathematicians independently of physics, seems to describe well the mysterious rules of the quantum world, rules that make no sense when viewed with an eye trained by our everyday experiences. So the physicist working with quantum systems relies on the mathematics to produce predictions of the outcomes of experiments or phenomena, since this same physicist has no natural intuition about what goes on inside an atom or a ray of light or a stream of particles. Quantum theory taxes our very concept of what constitutes science, for we can never truly understand the bizarre behavior of the very small. And it taxes our very idea of what constitutes reality. What does reality mean in the context of the existence of entangled entities that act in concert even while vast distances apart? The beautiful mathematical theory of Hilbert space, abstract algebra, and probability theory, our mathematical tools for handling quantum phenomena, allow us to predict the results of experiments to a stunning level of accuracy, but they do not bring us an understanding of the underlying processes. Understanding what really happens inside the mysterious box constituting a quantum system may be beyond the powers of human beings. According to one interpretation of quantum mechanics, we can only use the box to predict outcomes, and these predictions are statistical in nature. There is a very strong temptation to say, well, if the theory cannot help us understand what truly goes on, then the theory is simply not complete. Something is missing. There must be some missing variables which, once added to our equations, should complete our knowledge and bring us the understanding we seek. And in fact, the greatest scientist of the 20th century, Albert Einstein, posed this very challenge to the nascent quantum theory. Einstein, whose theories of relativity revolutionized the way we view space and time, argued that quantum mechanics was excellent as a statistical theory, but did not constitute a complete description of physical reality. His well-known statement that God doesn't play dice with the world was a reflection of his belief that there was a deeper, non-probabilistic layer to the quantum theory which had yet to be discovered. Together with his colleagues Podolsky and Rosen, he issued a challenge to quantum physics in 1935, claiming that the theory was incomplete. The three scientists based their argument on the existence of the entanglement phenomenon, which in turn had been deduced to exist based on mathematical considerations of quantum systems. At his talk at Berkeley in 1972, Heisenberg told the story of his development of the approach to the quantum theory called matrix mechanics. This was one of his two major contributions to the quantum theory, the other being the uncertainty principle. Heisenberg recounted how, when aiming to develop his matrix approach in 1925, he did not even know how to multiply matrices, an elementary operation in mathematics. But he taught himself how to do so, and his theory followed. Mathematics thus gave scientists the rules of behavior in the quantum world. Mathematics also led Schrödinger to his alternative and simpler approach to quantum mechanics, the wave equation. Over the years, I've followed closely the developments in the quantum theory. My books have dealt with mysteries in mathematics and physics. Fermat's last theorem told the story of the amazing proof of a problem posed long ago. God's equation was the tale of Einstein's cosmological constant and the expansion of the universe. The mystery of the Aleph was a description of humanity's attempt to understand infinity. But I've always wanted to address the secrets of the quantum. A recent article in the New York Times provided me with the impetus I needed. The article dealt with the challenge Albert Einstein and his two colleagues issued to the quantum theory, claiming that a theory that allowed for the unreal phenomenon of entanglement had to be incomplete. 7 decades ago, Einstein and his scientific allies imagined ways to prove that quantum mechanics, the strange rules that describe the world of the very small, were just too spooky to be true. Among other things, Einstein showed that, according to quantum mechanics, measuring one particle could instantly change the properties of another particle no matter how far apart they were. He considered this apparent
Sample complete. Ready to continue?